Okay, looks like I did some copy and paste here. So this last question, I'm going to change it. Prove using the series derived that the derivative of sine x is cosine x. Derivative of sine x is cosine x. Oops. That's right. Okay. So starting with the Maclaurin series for the sine function, I'm going to go back and pick that general formula that we had derived earlier. So this is a general formula for a Maclaurin series. As you can see, we need to know, first of all, the successive derivatives at 0. Once again, Maclaurin automatically means centered at 0. So we're going with this version. Our next example is going to be something about a Taylor series centered at a different point. Okay, so for this one, still Maclaurin, still centered at 0. So starting with f of 0. Since the function is a sine x function, this means sine of 0, which is 0. Okay. Now let me find the successive derivatives of this. F prime of x. Okay, derivative of sine x is cosine x. Second derivative is the derivative of cosine x, which is negative sine. I'm going to do a few of those in a row. Okay, we'll look at that website later. Okay, so the next derivative of sine is cosine, but because it's a negative, we have a negative cosine. Derivative of cosine is negative sine. Because of negative, we have positive sine. Notice we came back to the beginning. Now that we have sine x, from this point forward, everything is going to repeat itself, right? So like the next derivative would be cosine x. So we're back to the beginning. We're over here, etc. Now we want to evaluate each one at 0, at x equals to 0. What is cosine of 0? 1. Sine of 0 is 0. Cosine 0 is 1, except this is going to be negative 1, 0, and then 1. So the pattern seems to be 0, 1, 0, negative 1, 0, 1, 0, negative 1. Now let's put this pattern into the formula. Okay, so going with the formula above, sine x will be equal to, approximately speaking, actually we're going to put all the terms, so I'm going to just say it's equal to. Okay, okay, what is f of 0? F of 0 is 0, right? So the first term will be replaced with just 0. Okay, what is f prime of 0? That is 1, so we're going to have 1 times x over 1 factorial, or just x. Okay. The next one, f double prime, that will be 0. F triple prime, we have a negative 1 there, so I might as well erase my plus sign there and make it negative. 1 times x cubed over 3 factorial. Next one will be 0. What will the next one be? Now, the fifth derivative, right? The fifth derivative is back over here, is positive 1 times x to the 5 over 5 factorial. Now, let me just clean this up a little bit, right, without all the zeros in it. So this is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, etc. What will be the general pattern here? And I'm going to write that all on the bottom so I can have the whole line to use. So here's what we're saying. We're saying that sine x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And I want the generic term. Next one will be minus. First of all, it's alternating in sign, right? So how do you account for the fact that it's alternating in sign? What will you put here? negative 1 to the power of n or n plus 1. We can always play with that later. Okay, what will you write for the generic term? X to what? X to the, an odd number. Let's start with 2n plus 1 because our choices are like 2n plus 1 or 2n minus 1 divided by, you're still dividing by the same number, right? By the same odd number. So what would you put on the bottom? Still the same number, 2n plus 1, but with a factorial, right? Because it was like x to the 5 over 5 factorial. This will be x to the 2n plus 1 over 2n plus 1 factorial. How would you write then this in a compact sigma form? I'm trying to get rid of that for some reason. There's a demonstration on that side which I'd like to show you in just a little bit. Okay, so sine x then is equal to how can we write it in the compact sigma notation? Negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. Where would you start your n? You could try 0 or 1. I'm going to start with 0, see if that works. What would you get if n is 0? Negative 1 to the 0 is 1, so that gives you positive. 2n plus 1 would be just a 1. That gives you an x. On the bottom, a 1. Did we get just the first term there? We did. So this actually works. Second part of the question was, what is the interval of convergence for this series? What is the interval of convergence? How do we find it? Ratio test, as we've been doing all along. So to find the interval of convergence for part B, apply the ratio test. Anybody who did that and got an answer for us? Do you get infinity? If you did, a negative infinity to infinity, you were on the right track, absolutely. This is another series that converges for every x, which makes it very powerful, like for calculators, for tables that approximate sine function values. They can use it for any x. The only catch is add more and more terms the further away you are from 0. Okay, so we're going to use the ratio test. Limit as n goes to infinity of a sub n plus 1. Anyway, when I take absolute values, that negative 1 to the n will disappear. I don't even have to bother writing that. Tell me what I should write instead of x to the 2n plus 1 right now. Remember, you're replacing n with n plus 1. This is what it's going to look like, that 2n plus 1 you had earlier. So what did it become? 2n plus 3 divided by 2n plus 3 factorial and times 1 over a sub n. Okay, what is this limit? First, let's simplify it. X to the 2n plus 3 on the top, x to the 2n plus 1 on the bottom. What would you be left with on the top? What is the difference in these powers? If you subtract top power minus the bottom power, you get 2. So there's an x squared on the top, 2n plus 3 factorial on the bottom, and 2n plus 1 factorial on the top. Start expanding the bigger one, right? The 2n plus 3 factorial, how could you write that out? 2n plus 3, 2n plus 2, and below. And below part will cancel, right? So we'll be left with 2n plus 3 times 2n plus 2 on the bottom. Okay. Anything else? I think that covers everything. Remember, x is fixed. The only thing that's changing here is n, because we're taking a limit as n goes to infinity, right? So as n goes to infinity, the bottom is getting larger, therefore the ratio is going where? 0. Normally you set this less than 1 and you solve for x, but there is no x to solve for, just like the last problem, right? So what does that tell us? That the series converges for which x values? For all x. So this is less than 1 for every x, no matter what x is. Therefore, the interval of convergence is negative infinity to infinity once again. Okay. One of the first homework questions you have on your group activity is to do the same analysis we're doing here for the cosine function. It's going to be really similar. You're going to derive the series for the cosine function. But for the sake of this example, actually, I'm going to tell you what the cosine function is, because in a minute, we're going to try to prove derivative of sine as cosine. But you go back and do all the steps. I'm just going to give you the answer, but you still need to do the proof for how do you derive a series for cosine x. Just follow the steps from this problem. What was part C? Estimate sine of 0.5, correct? And then D, find the error using the alternating series estimation theorem. Okay, so first part C, we want to find sine of 0.5. Good question. Let's go back. Say, use the first 4 non-zero terms. Use the first 4 non-zero terms. Okay, to do that, let me remind everybody sine x. Sine x is at least the first 4 terms. We're going to use just the first form, so this is the first 4 terms. This is going to be an approximation. By the way, how many of you have heard of the fact that sine x is an odd function in trigonometry, like it's symmetrical with respect to the origin? Now look at the expansion of the sine function. What do you see? All the odd powers, right? Now in trigonometry, you learn cosine function is an even function. It's symmetrical with respect to the y-axis. Guess what? All the powers of the cosine function are going to be even numbers. So things we've learned in the past are confirmed, and then we can do a lot more with these power series expansions. Okay, let's first find sine of 0.5 using 4 operations. Because imagine not having this polynomial. We're stuck. You know, sine of 0.5, we couldn't do a single move there, right? How do you evaluate sine of 0.5 without a calculator? But now, again, we can see the function in more clear terms. Again, everybody knows how to cube something, like 0.5 times 0.5 times 0.5. We could do something even by hand if we had these 4 terms. Although we're going to still use a calculator to save some time, right? But at least we see what's happening. Okay, anybody who has a value for that? 0.4794. Can somebody else confirm it? Great. Kevin, you got it? Okay, 0.4794. Okay. Let's check it on the calculator. Make sure you're in radian mode, because this everything assumes radians. When you take derivatives of sine function in the proof here, derivative of sine is cosine only when x is in radians. So make sure you're in radians, and then the sine of 0.5. Although this question didn't ask for the calculator check, but just for our sake, wow, it matches all those first 4 digits, right? Again, we're very close to 0, so the answers are very accurate. The further away you go from 0, you will see the more terms you have to add. But this is just a side note that the calculator answer, even though for this question it was not asked for, but we were curious, right? And that was also sine of 0.5 equals 0.4794. Of course, it has more decimals, and they will differ at one point. Now, what this question did ask for, I believe part D said, estimate the error using the alternating series estimation theorem. Estimate the error using alternating series estimation theorem. Okay. That theorem said, if you use the first 4 terms, which term do you use for the error? in an alternating series, which this is. You use the next unused term for your error, right? So here we added the first 4 terms, and these are the first non-zero 4 terms. So we're going to use the next non-zero term for the error. So the theorem tells us that for an alternating series, the error will be less than the next unused term, which would be in this case what? 0.5 to which power? Remember, sine x only has odd powers, right? What would have been the next term on that series? To the 9th power divided by 9 factorial. This is going to be a really, really small error. 9 factorial is already a very large number. Let's see if anybody can evaluate that. 0.5 to the 9 divided by 9 factorial. And your factorial key is under Math Probability menu. Do you see something like e to the minus 9? So it's a very, very small error that we did very well here. So we get 5.38 e to the minus 9. So that's an extremely small error. So we know that this estimation, adding just the first 4 terms, is a really good estimation. Okay, I'm going to add a question here. Bump the other one to maybe F. Let this be part E. Okay, the question is the following. Okay. What is the largest value of x so that using the first 4 terms gives an error of less than 0.001. You know, here we use x equals 0.5, and we got a really, really good estimate. So I'm kind of changing the question around. Can we determine the largest value of x so that if we keep using these 4 terms, then we're still guaranteed with a pretty good approximation, something with an error less than 0.001. If we're going to use the first 4 terms, and we know this is an alternating series, then the error will be less than what? Excuse me, let me get rid of that. If you use the first 4 terms, then the error will be less than, up there we use 0.5 to the 9 over 9 factorial. Right now we don't know what x is, so we cannot put 0.5. So what should I put instead there? X. We don't know what that number is, so I'm going to put x to the 9 over 9 factorial. Now does everybody see why I'm using 9 and 9 factorial? Because we said we're going to use the first 4 terms, right? So the next unused term, because look at the first 4 terms of the series. X minus x cubed over 3 factorial, x to the 5 over 5 factorial, x to the 7 over 7 factorial. So if you're going to use the first 4 terms, the next unused term would be x to the 9 over 9 factorial. And you want this error to be less than what? 0.001, which is 1 over 1,000. Can you determine what x should be? What's the largest x can be? At the moment, assume it's an equal sign and solve for x. So basically, x will have to be that less than that value. So x to the 9 should be less than 9 factorial over 1,000. And x should be less than the 9th power, 1/9 power of that. Let's see what that is. Anybody who got something? 1.92 roughly, 1.925. That means as long as x is less than that value, you can still use just the first 4 terms, and you'll have a pretty reasonable estimate with an error less than 0.001. So you can see a calculator can easily be programmed to decide how many terms to add. And because calculators can only display so many digits, and for those number of digits that it displays, it can decide how many terms to add, etc. But for this particular question, if you're going to be adding only 4 terms, then go up to 2 roughly, or 1.93 roughly, and you'll still have a pretty good estimate there. Okay, I think I'm going to leave part E for you guys to do later on. Ask me about it. Remember, part E was derive sine as cosine, because part of your homework will be to derive the cosine function anyway, and then differentiate term by term, and we'll talk about it. It's going to be really beautiful to see that, derive sine as cosine without having to go into all sorts of theory. Like in Calc 1, you had to use a squeeze theorem. You had to do a geometrical figure and use limit definition. It was complicated to make that proof. Here it's going to be very, very simple. But I want to make sure that I do have enough time to do something about a Taylor series also today. And if we have time, we can come back to that question. Okay, let's answer the following question about a Taylor series. Okay. Find the Taylor series expansion. No. For e to the x centered at c equals to 3. By the way, on the last slide, there was a website that I wanted a quick demo there. So before we finish this question, there was a website there I want to show you. Right there. Let's see. Okay. Basically, what they have done is here, the blue curve is the sine x function, and you can enter just any number you want. It's the degree of the Taylor polynomial, in this case, the Maclaurin series, and it's going to graph it. Like right now, degree 1 is just a linear function. If you take just the first term of sine x, what would that be? Just the first term of sine x. What was it? Sine x equals, look back to that polynomial. What was the first term? Oh. The first non-zero term, that is. X, right? So what they did was for the first term, y equals x is this red line. You see how much is already just the y equals x is approximating this function for points around x equals 0. Now let's see what happens if you increase the degree. Okay, so let's say that we increase it to degree 3. It's expanded a little bit more around 0 right now. It approaches it even for further points, even up to 1. It seems like this is going to work well. Let's say 5. So it's approximating a little bit better. Let's just jump to something. Let's say 11th power. So already, it's going all the way to points like 3 and beyond. What if we do like something really high, like 27th power or something like that? So the more terms you add, basically, now you can't even see the distinction between that polynomial and that actual function. So the more terms we add, the closer we are getting to that approximation. Okay, going back to wherever we were. Okay. Okay. Now, for this one, look back to your notes. What was the Taylor series polynomial or Maclaurin series like? On the bottom of that handout, we had seen the general formula for the Taylor series centered at C. I'm going to copy that over. It was right here. Let me see if I can copy it. Okay, this was the Taylor series expansion for a polynomial. And let's go ahead and put it where we were, right here. Okay, so this is the Taylor series. Instead of x, you have x minus c. Instead of f prime of 0, you have f prime of c. Here c is 3. To be able to do this once again, you're going to need the successive derivatives. Start with f of 3, then do f prime of 3, but you need to know f prime of x first, etc. Okay, so if f of x is e to the x, what is f of 3? E to the third. The derivative is itself, right? So what is the derivative evaluated at 3? Also e to the third. So all the successive derivatives are going to be e to the third for this function. Again, we always start with something simple as our first example, and e to the x makes for a very simple example. Now let's put it together. So if you put into the compact notation format, it's going to look like this. The nth derivative at 3 times what? X minus 3 divided by n factorial. But usually I'll ask you to write this out for the first few terms. So let's write out the first few terms here. If n is 0, what would we get? 0 factorial is 1. The 0th derivative means the function itself at the point 3. So, excuse me, I forgot something in my previous one. What am I missing on the power of x minus 3 here? Right, look at the formula. I need the same thing, right? That's the general formula I'm copying over. I need an n there. Okay. So can you tell me what I'm going to get if n is 0? But instead of 1, we have e cubed, right? Because f of 3 was e cubed. So the 0th derivative is the function f of 3. Let's write it if you like. F of 3 times x minus 3 to the 0th power divided by 0 factorial. The second one will be f prime of 3 times x minus 3 to the 1st power divided by 1 factorial, and so forth. So what will my first term be this time? What is f of 3 for this question? F of 3 is e to the 3rd power, right? X minus 3 to the 0th is 1. 0 factorial is 1. So those are going to disappear. All you have is e to the 3rd. Plus, what is f prime of 3? F prime was here, right? All of these derivatives are going to be e to the 3rd for this function. Times x minus 3 to the 1st power over 1 factorial. What will the next term be? X minus 3 to the 2nd power divided by 2 factorial. And give me just one more. Etc. This is the expanded version, right? What we wrote earlier was the compact version. And if I want to use this, excuse me, I put x minus 2, I should have put x minus 3. If I want to use this for, say, estimate e to the 3.4, what would you get? E to the 3.4. Let's say that once again, use the first 4 terms, using the first 4 terms. Okay, the first term is a constant, e to the 3. The next one would be e to the 3 times what? What are we plugging in for x? 3.4. Now, guess why I gave you 3.4? I didn't give you 0.5 this time. Because when we had a Maclaurin series that was centered at 0, then I gave you a point close to 0 because I knew the estimation was going to be good there. If you have a Taylor series centered at 3, this is going to be really well for estimating points right around 3. And the further away you go from 3, the more terms you have to add to it. Okay. So in this case, plug in 3.4 everywhere you see an x. So you're going to have 3.4 minus 3 plus, in hindsight, I should have factored an e to the third power, right? But oh well. What should I be writing next? We are at this term right now. Point. Exactly. And what should I write for my last term? E to the third times 0.4 to the third over 3 factorial. Now 2 factorial is the same as 2, so no big deal there. Now you could go ahead and factor out e to the third. Notice that this will rely on knowing what e to the third is. So if you know that, then you can estimate values close to that, such as e to the 3.4, etc., like we're doing here. And if you do this, it's going to be very close to the calculator value. I can give you this right now. It's about 29.94 if my notes are correct from last year, so it should be 29.94. It should be pretty close to the calculator value there. Okay. So as always, I'm going to leave you with a homework problem to work on this Taylor series idea. One minute. Okay, let's do this one. Okay. Find a, let's see, use the first 1, 2, 3. Use the first 4 terms. So basically, it's going to be very, very similar question to this one that we have here. But instead of e to the x, use sine x and centered at pi over 6. So f of x will be sine x and centered at pi over 6. Pi over 6. Okay. Let's go ahead and finish this one, at least for our online students. And I modified the question a little bit. I made it find the first 4 terms of the Taylor series expansion for f of x equals sine x centered at pi over 6. Okay, so because this is going to be a Taylor series, we need to find the successive derivatives, but instead of plugging in 0, we're going to plug in pi over 6, right? So let's begin by, first of all, finding the successive derivatives of the sine function. So f of x is sine x. The derivative is cosine. Second derivative is negative sine x. The next one would be negative cosine x. And then we're back to the beginning of positive sine x. Okay. By the way, if you haven't tried it on your own first, it would be a good idea to pause the video for a little bit, try it yourself, and then watch the solution. I think you will get much more out of it that way. Okay, now we want to plug in pi over 6 for each one of these functions. So sine of pi over 6. Pi over 6 is 30 degrees, and sine of 30 degrees is 1/2. How about cosine of 30 degrees at pi over 6 radians? That would be radical 3 over 2, right? Negative sine of pi over 6, that will be negative a half. Negative cosine of pi over 6, that's negative root 3 over 2. And because there are no zeros here, and because that they're only asking for the first 4 terms, looks like I already have the first 4 non-zero values, so that will be sufficient. I don't have to go any further. But note that it would have been repeating itself after this point because we're back to sine x anyway. So the first 4 terms will keep repeating itself anyway. Okay, so now we want to write down the Taylor series expansion. First, I'm going to write the long form. So sine x for values close to pi over 6 is going to be equal to. The first one you want to look at is f of pi over 6. Instead of f of 0, we have f of pi over 6, and that was 1/2. Okay, the next one we want should be f prime of pi over 6 times x minus pi over 6 to the first power all over 1 factorial. And we know that f prime of pi over 6 is radical 3 over 2 multiplied with x minus pi over 6 and divided by 1 factorial. We get the same thing, no need to mention that. Okay, the next one will be the second derivative at pi over 6, which is negative a half, times x minus pi over 6 squared divided by 2 factorial. And the fourth and the last term would be, normally it should be the third derivative at that point, which is negative root 3 over 2 times quantity x minus pi over 6 to the third power divided by 3 factorial. And we only wanted to get the first 4 terms, so there we have it. All we can do is clean this up a little bit. For example, the last 2 denominators can be simplified. So this can be written as a half plus the square root of 3 over 2 times x minus pi over 6 minus x minus pi over 6 quantity square divided by 4 minus radical 3 over 2. Actually, I was going to simplify that. 3 factorial is 6. 6 times 2 is 12. That is my easy fix. Radical 3 divided by 12 times x minus pi over 6 to the third power. So this is not an alternating series because we have plus, plus, minus, minus. And notice that there is no clear pattern. This would have been quite difficult to try to write as a summation, but we don't have to do it because the question only asked us to write the first 4 terms. Okay. And here's one more for you to think about. Oh, that was the one we just did. Okay, let's just open a new page. So same question as before. We just want the first 4 terms. So I'm going to copy that from there. But a different function and different center. The function will be the cube root of x so let's enter it as x to the power of 1/3. So the cube root of x centered at the point c equals to 1. So once again, I want the first 4 terms of the Taylor series expansion, and I want you to use that to estimate the cube root of 1.28. And the good news is that you'll be able to check your answers on the calculator. At least, you'll have a relatively good idea about whether the answer you got using the Taylor series expansion is correct by checking your final answer on the calculator by taking the cube root of 1.28 on the calculator.